morning, sir. Good morning, sir. May I come, sir? Good morning, sir.
Good morning, sir.
May I come, sir?
Good morning, Captain.
Good morning, sir.
Happy New Year, sir.
Happy New Year. Good morning, sir.
May I come, sir? Good morning, sir. Thank you, sir. Good morning. May I come, sir? May I come, sir?
Sorry, interested.
हाँ ठीक है, लेकिन बाद में आना पड़ेगा फिर।
कोई बात नहीं।
इसमें कोई रिलैक्स नहीं होगा
ना
सर।
ना कोई May I come, sir?
गुड मॉर्निंग। यहाँ ये नाइट वाले में ले लिए थे।
नहीं नहीं मॉर्निंग का है ये
सामने
इन्होंने
हो रहा है ना।
ये इन्होंने साइन करवा लिए इन्होंने।
सामने पे
ꯑꯍꯥꯟꯕꯗ ꯑꯁꯦꯝ ꯑꯃꯔꯖꯤꯠꯅ ꯅꯔꯦꯟꯗ꯭ꯔꯅꯤꯡ ꯀꯔꯤꯒꯨꯝꯕ ꯃꯇꯝꯁꯤꯗ ꯑꯅꯤꯁꯨꯕꯗ ꯁꯟꯖꯟ ꯁꯛꯄ ꯑꯦꯛꯇꯤꯚ ꯁꯨꯕꯅ ꯁꯩꯔꯦꯡꯕ ꯏꯁꯩ ꯑꯍꯨꯝꯁꯨꯕꯗ ꯍꯨꯏꯊꯣꯛ ꯉꯥꯎꯕꯅ ꯁꯛꯄ ꯑꯦꯂꯥꯡꯕꯨ ꯏꯃꯥ ꯁꯛꯄ ꯑꯔꯣꯏꯕꯗ ꯂꯥꯏꯐꯣꯜ ꯒ꯭ꯔꯣꯁꯅꯤꯅ ꯁꯛꯄ ꯉꯥꯏꯔꯥꯡꯕꯨ ꯄꯔꯁꯟꯗꯨꯅ ꯁꯩꯔꯦꯡꯕ ꯏꯁꯩ
Sai mày để nuôi kia là mình nó thông sao luôn còn biết sao được đâu tôi nó tiền sân bản nó không có cái nào lên kìa
May I come, sir?
अनिल जी गुड मॉर्निंग। अनिल जी
गुड मॉर्निंग सर।
प्लीज स्टार्ट द क्लास।
शतबी गुरबो। हाँ सर मैं
अनिल
कर
जी।
रहा हूँ, मैं प्रेजेंटेशन दे रहा हूँ उसके बाद सर कर रहा हूँ।
हाँ हाँ। अदर्स आर रिक्वेस्टेड टू प्लीज म्यूट।
Good morning, sir.
अनिल जी प्लीज स्टार्ट द क्लास।
नमस्कार सर।
उसको गुड मॉर्निंग।
Okay, good morning to all. Myself Anil Kumar, PGT Physics, JNU Morigaon. So today we will study two chapters, that is electromagnetic induction and alternating current. So first of all, we are going to start electromagnetic induction. So in this chapter, we will study about magnetic flux, eddy current, and Lenz law, motional EMF, and self and mutual inductance. So let us start first. Uh, विटामिन डालो थोड़ा टेक्निकल प्रॉब्लम आ रहा है मैं थोड़ा देखना उसको Okay, so what is magnetic flux? As you know, we have magnetic field, and around magnetic field we have magnetic field lines, and magnetic flux is defined as the uh, magnetic flux through any surface is the number of magnetic field lines of force passing normally through that surface. For example, if we have a unit area and four magnetic field lines are passing through that area, and another area that is 1 centimeter square, and that area 10 magnetic field lines are passing through. So the second one has the more magnetic flux. You can see in the figure we have a small area ds and a magnetic field b. So the component of ds, that is area vector making an angle theta with the magnetic field. So the magnetic flux can be defined as the dot product of magnetic field and the small area ds. So magnetic field can also be defined as the product of area of the surface and the component of the magnetic field normal to that surface. So in this slide, you can see that the magnetic flux is given by B dot A cos theta, and magnetic flux across a coil can be changed by changing. So as the formula indicates that the magnetic flux depends on the magnetic field area and the angle between magnetic field and area vector. So we can change the magnetic flux by changing the strength of the magnetic field B and the area of cross section of the coil A. The orientation of the coil with the magnetic field theta, as we generally do in generator. When we change the angle theta, we change the magnetic flux and producing current. And we can also change the magnetic flux through any combination of the above. That is, we can change the magnetic field as well as the area. We can change magnetic flux by changing the area as well as the angle. So in this way, we can change the magnetic flux across a coil. Now, the magnetic flux is a scalar quantity. Okay, it has no direction. So SI unit of magnetic flux is Weber or Tesla meter. You must know about the SI units of this because in MCQ he may ask. And in CG system, the magnetic flux is Maxwell, and 1 Maxwell is equal to 10⁻⁻8 Weber. Okay. So Faraday do experiment to produce magnetic flux, to produce current by changing the magnetic flux. In this first experiment, you see a magnet and two coils. So when we move the magnet towards any coil, the magnetic flux linked with the coil changes and produce current. You see in this figure, first figure, the direction of the magnetic current is anti-clockwise. Okay, and in this figure, the current direction is clockwise because the opposite poles of the magnet faces the two coils. And if we change the magnet orientation, so you can also see that in the first figure, previously the direction of the current was anti-clockwise. Now the when we change the direction of orientation of the magnet, the direction of current will change to clockwise. So we can change the direction of current by changing the orientation of the magnet. Now, in this figure, you see that when we bring the magnet towards the coil, the magnetic flux is changing. The magnetic flux is increasing actually. So the magnetic flux between the coil changes relative to the position of the coil and the magnet is a magnetic line of forces cutting at different angles at the same cross-section area of the coil. So we can increase or decrease the magnetic flux by to and fro motion of the magnet and generate current in the coil. And the galvanometer will show the direction of the current. From the above experiment, first we observed that the relative motion between the coil and the magnet, the induced polarities of magnetism in the coil, and the direction of the current. So when we observe that the relative motion between the coil and the magnet will induce current. First observation we have done, and the second induced polarities. That is, the direction of the current changes when we move the magnet towards the coil, and when we move the magnet away from the coil. So direction of the current changes. Okay, so these observations we have made, and that the induced EMF is available only as long as there is a relative motion between the coil and the magnet. Magnet is stationary, there is no current in the coil. So the fourth observation that the induced current EMF is a relative motion between the coil and the magnet. So from now in the second Faraday's experiment, he replaced the magnet by a solenoid. Okay, you can in the second solenoid we have a galvanometer only. There is no source of electric current. So when we switch on the battery, which on the battery will generate its magnetic flux. As you know, the Lenz's law, the magnetic field is changing in this first coil. So due to this changing of magnetic flux, the current produced in the second coil, which is connected to a galvanometer battery. So we can also change the polarity of the by night. In the first figure, you can see that here is a south pole and north pole, and when we change the direction of current, then we have no current in the first coil. We can change the polarity on the solenoid of the second coil. So 0 to maximum value, and during the period changing current induces changing magnetic flux across the primary coil. This is changing magnetic flux linked across a secondary coil and induces a reflection in the galvanometer lasts only as long as the current in the primary coil, and hence the magnetic flux in the secondary coil change the current in the first coil. There is no induced EMF or current in the second coil. So in this way we observed many things. Now zero value, and during first this period changing current induces changing magnetic flux across the primary coil. So when you switch off the primary circuit, it will not give to a little bit slower, and due to which the current changes and magnetic flux changes, due to which in the second coil Now, Faraday's based on these observations, Faraday's give two laws. That is Faraday's laws, electromagnetic induction. That is in the magnetic flux linked with the circuit and EMF, and hence a current I is induced in the circuit. However, it lasts so long, just from above to observations. That is, whenever there is a change in the magnetic flux linked with the coil, linked with the circuit and EMF, and hence a current is induced. At to and fro, there is the induced EMF in the circuit. And in the second case, we have seen that when we switch on enhance EMF in the secondary coil, and we also observed that it was last as long as the motion of the magnet and the the change of magnetic flux, and the rate of change of magnetic flux linked with the circuit. That is by changing of magnetic flux. So in this second law, he finds an expression, or EMF is directly proportional to the rate of change of magnetic flux. Okay. So in this equation, you can see that when the sign and we have chosen the unit of K such that we will get E is equal to dψ by dt. Okay. Now, very important law, that is Lenz's law. Based on this law, many questions comes in MCQ. So let us first study this law. What is Lenz's law? The direction of the induced EMF, the change that is producing it. Okay, in the first experiment, we see that when the magnet comes to and fro from the coil, the current induced in the coil. Okay, now this law states that the motion of the magnet will be opposed by the induced current, because the reason for producing this law, the induced current will oppose the motion of the magnet. If it is coming towards the coil, it will oppose the forward motion, and if the magnet is moving up, so let us study more. Either the current is induced due to motion of the magnet, then the induced current in the coil sets itself to stop the motion of the magnet, oppose the motion, forward motion, as well as if the magnet is moving backward, it will also oppose the backward motion. Now to the change in current in the primary coil, and the induced current is such that it tends to stop the change. In case of solenoid, if we are producing induced current using another solenoid, then the cause for it, that is the current is such that tends to stop the change. Okay. Now Lenz's law and law of conservation of energy. This question, that is, what is Lenz's law and how it is associated with the law of conservation of energy. Okay. So according to the Lenz's law, the change in magnetic flux, what is it? It is the opposition which we perform magnetic. according to the Lenz's law, the induced EMF opposes the change that produces it. It is the opposition, the change in magnetic flux. Therefore, mechanical energy is converted into electrical energy. Thus, Lenz's law is in accordance with the law of conservation of energy. Okay. इसको examples से समझते हैं. If, however, the reverse would happen, either the induced EMF does not मैं भी क्लास कर रहा हूँ. ठीक. Okay, so according to Lenz's law, the induced EMF opposes the change that produces it. It is the opposition against which we perform mechanical work in causing the change in magnetic flux. अगर हम लोग मैग्नेट को मूव कर रहे हैं तो उस मैग्नेट को मूव करने के लिए हमें मैकेनिकल वर्क करना पड़ रहा है ना, एंड दैट मैकेनिकल वर्क इज कन्वर्टेड इनटू इलेक्ट्रिकल एनर्जी. सो वी कैन सी दैट the Lenz's law is in accordance with the law of conservation of energy, because our mechanical work is totally converted into electrical energy. In this way, we can say that the Lenz's law is in accordance with the law of conservation of energy. Now, there is one question based on Lenz's law. What is the magnitude of the induced current in circular loop KLMN of radius R if the straight wire PR and increasing current from P to R? Yeah. Solve this question and give me answer. किया. So in this question, you can see that we have a current loop KLMN of radius R. Okay, and below this wire PR is there, and in the first case there is a steady current of magnitude I. So we see that when the magnet is stationary, the current is steady. So we don't have any induced current in the loop KLMN. Okay. Now in the second case, we have a current, increasing current from P to R. So first of all, we have to find the direction of magnetic field due to this increasing current P to R. So when you apply right hand thumb rule on that current is perpendicular to the plane and it's outward. So to oppose that magnetic field, the direction of the current in the loop KLMN should be in such a way that the magnetic field produced by the induced current will oppose the magnetic field due to increasing current. So now give me the direction of the current in the loop KLMN. Anyone? Okay, no problem. So in the first case, we have 0 because steady current produces the current magnetic field. There is no change in magnetic flux. Okay, and the second answer, as per the right-hand thumb rule, magnetic field due to current carrying wire PR acts on the loop in a direction perpendicular to the plane of the paper and it's outward. So, according to the Lenz's law, the direction of the current in the coil must be opposed this magnetic field. So, the induced current in the loop must flow clockwise to oppose the magnetic flux. So, that type of questions is very much important because in previous years you can see in question paper and MCQ he asked the direction of the current. Okay, many like I mean, I'm trying to activate my pen. Okay, no problem. So in your you have sample papers. In your sample papers, you can find there is a many ways to produce induced current. In the first figure, you see we are using a magnet, and the second figure, you see that we are using a magnet and two coils. So when we move the magnet forward, you can see the south pole of the magnet is towards the first coil and the north pole of the magnet is towards the second coil. So when we, as the figure shows, the motion of the magnet is opposed by the induced current coil. There must be a south pole, okay, so that it will oppose the forward motion. So for south pole we have the direction of current in clockwise direction. So in the coil 1, the direction see that when we move the magnet towards the first coil, the north pole is moving away from the second coil. So the pole in the second coil must be south pole. Okay, so south pole because south pole will attract north pole and it will oppose the direction motion of the magnet backward. So for south pole we should have the direction of magnet the current is clockwise. Okay, you can see here also we are using two coils. We have seen induced current in the nearby coil also changes. Now expression for the induced EMF based on these two laws. Now as we know that the induced EMF is equal to minus d/dt, that is rate of change of phi 2 minus phi 1 by t. Okay, now we know that the current is I is equal to V by R. So in the expression for induced current must be I is equal to minus d phi by dt by R. Okay, now expression for charge, what dq is equal to minus phi d phi by R. Okay, now this is the EMF generated in the second coil. This is the expression for the EMF generated in the second coil or induced methods of producing induced EMF. There are various methods we can induce EMF in the nearby coil. First is by changing the magnetic flux. So magnetic flux can be changed by changing the magnetic field. So we can change the magnetic field B, and second by changing the area of the coil, that is motional EMF. We can change the area of the coil by changing the by changing the velocity of the wire. For example, we have a coil here, P dash, Q, R, and S dash, okay, which is moving towards this area of uniform magnetic field. So we can, when the area is coming inside the magnetic field, the magnetic flux is increasing, okay, and we know that the magnetic flux is given by B dot dA. So the small increase in magnetic flux is given by d phi is equal to B dot dA, okay. Now the area is increasing, okay, so we can write this area as V into dt. This length is V into dt into L. V into dt into L is the area increase in time dt. So the motional EMF will become, the changing magnetic flux will become BLV dt. Now by the formula of induced EMF, that is E is equal to minus d phi by dt, we will get E is equal to minus BLV. Okay, so BLV is the motional EMF. We can see that by changing the flux or by changing the area, we are producing induced EMF, and the value of induced EMF is given by BLV, that is magnetic field length and velocity of the coil, which is moving towards the uniform magnetic field. So the loop PQRS is slided into the uniform and perpendicular magnetic field. The change increase in area of the coil under the influence of the field is dA in time dt. यानी कितना एरिया इंक्रीज हुआ उसका टाइम dt में dA. This causes an increase in the magnetic flux d phi. So the induced EMF is due to the motion of the loop, and so is called motional EMF. And if the loop is pulled out of the magnetic field, then the induced EMF is given by BLV. The direction of the induced induced current is anti-clockwise in the loop P dash S dash R dash Q dash P dash. इसमें अभी हमारे पास जो लूप है अगर वो बाहर की तरफ आएगा, है ना, is moving out of the magnetic field. So according to the Lenz's law, the changing magnetic flux will oppose that motion. Okay, so the direction of the current will also changes. So according to the Lenz's law, the direction of the induced current is such that it opposes the cause for changing magnetic flux. Hence, here the cause of changing magnetic flux is due to the motion of the loop and increase in area of the coil in the uniform magnetic field. Therefore, this motion of the loop is to be opposed. So the current is setting itself such a way that by Fleming's left-hand rule, the conductor arm PS experiences a force to the right where the loop is trying to move towards the left. Okay, so when we move this when we move this coil out of this magnetic field, so the direction of the current in such a way that the force, according to the Fleming's left-hand rule, the force will oppose the velocity which is going outward. The force and the velocity must be in opposite direction. In that way, we can find the direction of the current. So, you know the what is Fleming's left-hand rule? Okay. Now, the third method is by changing the orientation of the coil. By changing the orientation of the coil theta in the magnetic field. This is the method of generating EMF in AC current also, AC generator also. So, magnetic flux can be changed by changing the relative orientation of the loop theta with the magnetic field B, and hence EMF can be induced in the coil. For example, you can see here uniform magnetic field B is there, and coil PQRS is there, and we are rotating it with a angular velocity omega. By rotating the coil, we are changing the angle between the area vector and magnetic field. So, as we know that the magnetic flux is given by n turn the number of coils, that is NBA cos theta. If we are rotating the coil with a angular velocity omega, then theta is equal to omega t, and our expression will become phi is equal to NBA cos omega t. Now, in order to find the induced EMF, we have to differentiate it. So, when we differentiate, we will get minus NBA omega sine omega t. Okay. Now, the final expression comes out to be NBA omega sine omega t. So, this expression will give you a induced EMF in the coil, and we can replace that is NBA omega by E naught. So we will get the equation for alternating EMF, that is E is equal to E naught sine omega t. So you see that by changing the orientation, we can generate induced EMF in the coil, that is E is equal to E naught sine omega t. You can see here in the first graph, there is a change of induced EMF. First, when the direction of the when the direction of magnetic field and the area vector is parallel to each other, that is 0, we have 0 EMF. And when the direction increases to the angle between them increases to 90 degree, we will get maximum EMF, and it will change as per the rotation of the coil. Okay. In the first graph, we have sine waves, and in the second graph, we have cos wave. Okay. If the initial position of the coil is taken as 0, either the normal to the coil is at 90 degree with the magnetic field, then theta becomes theta plus pi by 2, and the equation will change from E is equal to E naught sin omega t to E is equal to E naught cos omega t. You can see that here we have E naught sin omega t, but if we change the orientation theta by theta plus pi by 2, you will get the induced EMF as E is equal to E naught cos omega t. So alternating EMF and consequently alternating current can be expressed in sine और cos function. हम लोग दोनों में से किसी में भी इसको रिप्रेजेंट कर सकते हैं, ऐसे कोई कंपल्सरी नहीं कि हम लोग हमेशा इसको साइन वेव्स में ही रिप्रेजेंट करें. This method of introducing EMF is basic principle of generator. So we will study this during the topic of AC generator also. Now eddy current. What is eddy current? The induced circulating looping current is produced in a solid metal due to change of magnetic field. Magnetic flux in the metal are called eddy currents. So eddy currents have some applications and has property. It has a heating effect, and it always opposes motion. Okay, and this eddy current also generate by changing magnetic flux. Okay, so what is the applications of eddy current? An induction furnace eddy current are used for melting iron ores, etc. In speedometer, eddy currents are used to measure the instantaneous speed of the vehicle, and in deadbeat galvanometer, eddy currents are used to stop the damping of the coil in a shorter interval. Okay. in case of galvanometer, if we don't have any eddy current, the needle will show deflection. In electric brakes of the train, eddy currents are produced to stop the rotation of the axle of the wheel. Okay, in trains we use generally eddy currents to stop the train as electric brakes. In energy meters, that is watt meter, eddy currents are used to measure the consumption of electrical energy. It was used previously. Now we have digital meters. So previously we have a electric meters based on eddy currents. In diathermy, eddy currents are used for localized heating of tissues in human bodies. Okay, it is used for determining eddy currents for giving heat to the tissues of human bodies. Now, next topic is self-induction. One question from self-induction or mutual induction may come this year because from many years it is not come in the exam. So, what is self-induction? Self-induction is the phenomena of inducing EMF in the self coil due to change in current and hence the change in magnetic flux in the coil. Okay, when the current passes through the solenoid or a coil, the due to self-induction, there is a EMF produced in the coil. Okay, the induced EMF opposes the growth or decay of the coil, decay of the current in the coil, and hence delay the current to acquire the maximum value. Because of self-induction, when we pass the current through any coil, it will not go its maximum value at that time. It will go slowly, and when we switch off the current, it will comes to its minimum value. Okay, not instantly. It will decrease slowly. So it is the property of self-inductance, that is the induced EMF opposes the growth of or decay of the current in the coil and hence delays the current to acquire the maximum value. Self-induction is also called inertia of the electricity as it opposes the growth or decay of the current. Okay, another name of the self-induction is inertia of the electricity. So we have to find the self-inductance for a coil. So what is self-inductance for a coil? The magnetic field. We know that the magnetic field at any point due to a current carrying coil is directly proportional to the current. So the magnetic flux is proportional to the current. Okay, because magnetic field is directly proportional to current, so the magnetic flux is also directly proportional to the current. And when this proportionality sign is removed, we will get a constant L. That is phi is equal to Li, where L is the constant of proportionality and is known as self-inductance or coefficient of self-induction. Okay. Now to define this self-induction, we will take I is equal to 1, so L becomes equal to phi. Thus, we can also define self-inductance as the magnetic flux linked with the coil when unit current flows through it. Okay. So alternatively, we can define self-inductance as the magnetic flux linked with the coil when unit current flows through it. Okay. Also, we have induced EMF as E is equal to minus d phi by dt. So we will get, when we put the value of phi here, we will get E is equal to, that is induced EMF is equal to minus L di by dt. Okay. So this EMF will oppose the decay and the growth of the current in the circuit. It is a property of self-inductance. Okay, and when the rate of change of this current is 1, then L is equal to E. So we will get another definition. We can also define the self-inductance is defined as the induced EMF set up in the coil, though which the rate of change of current is unity. Okay, अगर rate of change of current is unity है, तो हमारा self inductance है वो किसके इक्वल हो जाएगा? Induced current के इक्वल हो जाएगा या induced EMF के इक्वल हो जाएगा. Okay. Now, SI unit of self-inductance is Henry. Okay, so the self-inductance is said to be 1 Henry when 1 ampere of current in the coil links magnetic flux of 1 Weber. यानी एक कॉइल से अगर 1 एम्पियर करंट फ्लो कर रहा है और वो 1 वेबर की मैग्नेटिक फ्लक्स प्रोड्यूस कर रहा है, तो हम लोग बोल सकते हैं कि इस कॉइल का जो सेल्फ इंडक्टेंस है वो 1 हेनरी है. और अल्टरनेटिवली वी कैन ऑल्सो डिफाइन सेल्फ इंडक्टेंस इज सेड टू बी 1 हेनरी व्हेन द यूनिट रेट ऑफ चेंज ऑफ करंट induces EMF of 1 volt in the coil. Okay, any one definition will work. You can write any one out of two. So now we have to calculate the self-inductance of a solenoid. So in order to calculate the self-inductance of a solenoid, we have a solenoid of length L and a number of turns per unit length as N. So we know that the magnetic field inside the solenoid is given by B is equal to mu naught Ni. Okay, so the flux linked with the coil, each coil is given by BA is equal to mu naught Nia. Okay, if we replace small n by capital N, so the expression will become mu naught Nia divided by L. Okay, so the magnetic flux linked across n number of turns of the coil will comes out to be mu naught n square Ia. Okay, we have calculated the flux as mu naught Nia. Now we are calculating the flux through n number of turns. So we will get mu naught n square Ia by L. Now by the definition we have phi is equal to Li, and when we equate these two equations we will get L is equal to mu naught n square A by L, or alternatively we can write it as mu naught n square Al. So this is the expression for the self-inductance of the coil. So in this derivation you can remember this formula for the numericals, because with this derivation we will get one numerical also. So if in the question number of turns and area and length is given, we can easily find the self-inductance of the coil. Now next topic is mutual induction. So what is mutual induction? As you studied earlier in your 10th class during the function of this electric generator. So mutual induction क्या है? What is mutual induction? Mutual induction is the phenomena of inducing EMF in the secondary coil due to the change in current in the primary coil, and hence the change in magnetic flux in the secondary coil. I'm reading it again. Mutual induction is the phenomena of inducing EMF in the secondary coil due to change in current in the primary coil, and hence the change in magnetic flux in the secondary coil. यानी हम लोग प्राइमरी कॉइल से करंट को पास कर रहे हैं, तो इस केस से जो मैग्नेटिक फ्लक्स चेंज होगा उस मैग्नेटिक फ्लक्स की वजह से सेकेंडरी कॉइल में करंट इंड्यूस होगा, और करंट इंड्यूस होने से उसका भी मैग्नेटिक फ्लक्स चेंज होगा. दिस phenomenon is known as mutual induction. So as we describe self-inductance, again we are introducing mutual induction, that is the flux is linked with the current. Flux is directly proportional to the current, and when we remove this sign of proportionality, we will get another constant, that is m, where m is the constant of proportionality and is known as mutual induction or coefficient of mutual induction. If the current is 1, then we will get m is equal to phi. That is, we can now define mutual inductions in another way also. Mutual induction is defined as the magnetic flux linked with the secondary coil when unit current flows through the primary coil. Okay, so in terms of induced EMF, we can write as E2 is equal to, that is induced current in the secondary coil, is equal to minus change of flux due to the first coil by dt. Okay, and we will get E2 is equal to minus m di by di1 by dt, and that is current flowing in the primary coil. Okay, and we will put the value of di1 by dt as 1, so we will get m is equal to E, and we can define again mutual inductance as the induced EMF set up in the secondary coil when the rate of change of current in the primary coil is unity. Okay, and the SI unit of mutual induction is also Henry. So mutual induction is said to be 1 Henry when 1 ampere current in the primary coil links with magnetic flux of 1 Weber across the secondary coil. Okay, how can we define 1 Henry? You can define 1 Henry as per self-induction or mutual induction, both are same. But in mutual induction, 1 Henry of in mutual induction is said to be 1 Henry when 1 ampere current in the primary coil links with the magnetic flux of the Weber across the secondary coil. Here, the definition is little bit different because here is two coils. In self-induction, we have only one coil. So in this definition, we have to connect primary coil with the secondary coil. For example, let us read it again. Mutual induction is said to be 1 Henry when 1 ampere current in the primary coil links magnetic flux of 1 Weber across the secondary coil. Now, now we have to calculate the mutual induction of two long coaxial solenoids. Okay, here we have two solenoids, so we have to calculate the mutual induction between the two coils. So first of all, the magnetic field due to primary solenoid is given by B1 is equal to nu naught N1 I1. Okay, this is the magnetic field linked with the primary coil from where the current is passing through. Now the magnetic flux linked across one turn of the secondary coil is the magnetic field is produced by the primary coil, and the secondary coil is placed in the magnetic flux linked with the first coil. Okay, now the magnetic flux is given by B1A, that is the magnetic field due to coil 1 into area. So we will get the magnetic flux as nu naught N1 I1A. Okay, and the magnetic flux linked with N2 turns of the secondary coil. This is the magnetic flux produced by the first coil, and this flux is linked with the N2 terms of the secondary coil. So the magnetic flux linked with the secondary coil will comes out to be nu naught N1 N2 I1A by L. Okay, now by definition we have phi 2 1, that is a magnetic flux linked with second coil due to 1 is given by M21 I1. Okay, by equating these two expressions we will get the value of M21, that is M21 comes out to be nu naught N1 N2 A by L. Okay, in terms of number of turns, but in terms of number of turns per unit length we will get nu naught N1 N2 A L. Okay, now similarly we can find the mutual induction of coil 1 with respect to 2, that is M12. Likewise, if we pass the current from secondary coil and the induced current will produce in primary coil, so the expression will comes out to be nu naught N1 N2 AN, same expression, same. Okay, so for the two coaxial solenoid of the same length and cross-sectional area, the mutual induction is same and leads to the principle of reciprocity. Okay, that is M is equal to 1, M12 is equal to M21. अगर दोनों में सब कुछ सेम है, करंट सेम है, एरिया सेम है, लेंथ सेम है, तो दोनों का जो म्यूचुअल इंडक्शन होगा वो सेम होगा. Now there is some additional information. If the two solenoids are wound on magnetic core of relative permeability nu, okay, then the mutual induction will little bit modified, that is M is equal to nu naught nu r N1 N2 A by L. And if the solenoids S1 and S2 have number of turns N1 and N2 or of different radii R1 and R2 such that R1 is less than R2, then the magnetic induction will little bit modified, that is nu naught nu r N1 N2 divide pi R1 curve square divided by L. And mutual induction depends also on relative placement of the solenoid. And the coefficient of coupling K between the two coils having self-inductance L and L2, then the mutual induction M becomes K is equal to, sorry, the coefficient of coupling K is given by K is equal to M by square root of L1 L2. Okay. If we have two inductors, that is two solenoids of inductance L1 L2 in series, so the equivalent impedance is given by L1 plus L2. And if we have two inductors in parallel, so the equivalent impedance is given by 1 by L1 plus 1 by L2. Okay, so this was our chapter EMI. Now let us start. Now let us start alternating current. Okay, so after this electromagnetic induction, we have another chapter, that is alternating current. So first of all, we have to know what is alternating EMF. So an alternating EMF is that EMF which continuously change in magnitude and periodically reverse its direction. Okay. Likewise, alternating current is also defined as, that is, alternating current is that current which continuously change in magnitude and periodically reverses direction. You can see in these two graphs. In first, we have represented the alternating EMF and alternating current in sine waves. It starts from 0 and will become maximum at pi by 2. Okay, and again minimum at pi, and again maximum at 3 pi by 2, and so on. But in case of cos waves, it attains its maximum value at 0
इसको तो ऐसे
and
रखना,
minimum value at pi by 2.
इस पे जिसका साइन नहीं है साइन
So it changes direction and magnitude periodically. That's why
जिसका नहीं
they are called alternating EMF and alternating current. Okay, where E and I are the instantaneous values of EMF and current, and E0 and I0 are the peak or maximum values of the EMF and current. So here the symbol of the symbol for AC source is like given by this. Okay, you can see here there is a circle, and in circle we have a Z. This is the symbol for source of. So if the source is EMF, alternating source is used. Okay. Now our second topic is average or mean value of alternating current. So what is the average or mean value of alternating current is? The average or mean value of alternating current over a half cycle is that steady current which will send the same amount of charge in a circuit in the time of half cycle as it sent by the given alternating current in the same circuit in the same time. I am reading it again. Average or mean value of alternating current over half cycle is that steady current which will send the same amount of charge in a circuit in the time of half cycle as is sent by the given alternating current in the same circuit in the same time. So here the time period is half cycle. according to the average or mean value of alternating current, we have to calculate the charge supplied by steady current and the alternating current during half cycle in the same time in the same circuit. So first of all, by the definition of current, we have I is equal to dq by dt. So dq will become equal to I into dt, because we are studying alternating current. So the current will replace by alternating current, that is I is equal to I naught sin omega t dt. So the total charge passed during the half cycle, that is 0 to t by 2, we have to calculate, that is q is equal to 0 integration of 0 to t2 t by 2 I naught sin omega t dt. Okay, when we integrate it, we will get I naught minus sin omega t, okay, by omega. And when we put the limits, upper limit minus lower limit, we will get q is equal to 2 I naught by omega. Okay, and when we put the value of omega here, we know that the value of omega is 2 pi by t. So this expression will modify to 2 I naught t by 2 pi. Okay, and when we cancel out the common terms, that is 2, we will get I naught t by pi. Okay, so if we let the value of mean value of AC is IAV, na? So IAV is equal to Q by T by 2, because the time period is T by 2 half cycle. Okay, when we equate these two equations, that is Q is equal to I naught T by pi and Q is equal to IAV by TM, we will get IAV या फिर IAM as 2 I naught by pi. Okay, when we solve this, we will get 2 by pi value as 0.637 I naught. Okay, so we can say that the mean value of alternating current is 63.7 times of its maximum current. ठीक है, जो हमारे पास मीन और एवरेज वैल्यू ऑफ करंट है वो 63.7% ऑफ मैक्सिमम करंट होगा, दैट इज आई नॉट. Likewise, we can also show that the average or mean value of the alternating current is also 63.7% of the maximum induced EMF, sorry, maximum potential E naught. Okay, the average or the mean value of the alternating current or EMF is 0 over a cycle, as the positive and the negative values get cancel out. अगर हम इसको पूरे फुल साइकिल में कैलकुलेट करेंगे तो ये 0 आएगा, बिकॉज पॉजिटिव एंड नेगेटिव वैल्यूज कैंसिल आउट हो जाएगी. इसलिए हम लोग मीन और एवरेज वैल्यू को हमेशा हाफ साइकिल में कैलकुलेट करते हैं. ओके, so you have to remember that the mean or average value of current is equal to 63.7% of its maximum value, and average and mean alternating voltage or EMF is also 63.7% of its maximum value. Okay, now next topic is root mean square or virtual or effective value of alternating current. Name is same, that is root mean square value of alternating current. Okay, so what is root mean square value? That is RMS value of alternating current. That is root mean square value or root mean square value of alternating current is that steady current which would produce the same heat in given resistance in a given time as it's produced by the alternating current in the same resistance in the same time. So the root mean square value is associated with the heat produced in the resistance, okay, in the same circuit in the same time by steady current and alternating current. So we know that according to the Joule's law of heating, the heat produced in a conductor is equal to I square R dt. So the small heat produced in the conductor is given by I square R dt, and when we put the value of I as I naught sin omega t, we will get I naught का square R sin square omega t dt. So if we calculate the heat generated in over a complete cycle, that is from 0 to t, we have to integrate this expression from the limit 0 to t. So h is equal to integration 0 to t I square r sin square omega t dt. In this expression we have I square r constant, so it will come out of the integration sign. If we integrate sin square omega t dt, we have to change it in another form because we cannot integrate sin square omega t, so it will comes out to be 1 minus cos 2 omega t by 2. Okay, and we know that the integration of cos 2 omega t over a complete cycle 0 to t is 0, so we will get the value of heat generated over a half cycle, over a full cycle, as I square r t by 2. Okay, and if IV is the virtual value or the mean RMS value of alternating current, so the heat generated by this virtual value of AC current is given by H is equal to IV square RT. Okay, because according to the definition or the explanation, root mean square value, the two heats must be same. That is, the heat generated by the steady current and the heat generated by the alternating current must be same. So if we equate these two expressions, we will get the IRMS value or the effective value of the current as I naught by square root 2, or 0.707 I naught. In terms of percentage, we will get 70.7% of I naught. So the IRMS value of alternating current is about 70.7% of the maximum current, peak value of the current. Okay, you must remember that is the average value of the current is equal to 63. You can see here 63.7% of the maximum current. Okay, and IRMS value of the alternating current is about 70.7% of the maximum current I naught. Okay, likewise the ERMS value of the alternating voltage is equal to 70.7% of the maximum value of alternating voltage, that is E naught. So note, the root mean square value of the alternating current or EMF can be calculated over any period of the cycle, since it is based on the heat energy produced, है ना. हीट कभी कैंसिल नहीं होगी. अगर हम हाफ साइकिल में देखें, सोचें कि अगर हाफ साइकिल में हीट जो है वो निकल रही है, एक्सोथर्मिक रिएक्शन है, और अदर हाफ में एंडोथर्मिक रिएक्शन है, दोनों कैंसिल आउट हो जाएगा, तो ऐसा नहीं है. ठीक है, हीट जनरेट होगी दोनों में और हम लोग उसको कैंसिल नहीं कर सकते, इसलिए इट कैन बी कैलकुलेट ओवर एनी पीरियड ऑफ टाइम, एनी साइकिल, हाफ साइकिल, फुल साइकिल, 1/4, किसी भी हम लोग कैलकुलेट कर सकते हैं, इसमें कोई ऐसी डिफिकल्टी नहीं है. ओके, so you must remember the root mean square value of the current, alternating current, is equal to 70.7% of the maximum current. Okay, now in this figure you can see both the values, that is the RMS value and the average value. Okay, E naught is the maximum value of the alternating voltage, and as we know that the IRMS value is 70.6%, 70.7%. So it is represented by this green EV, green line, and EM is the average value. It is about 63.7% of the maximum value. So in this graph, it is shown that the root mean square value and the average value with the peak current, peak voltage, that is E naught. This gives the values of alternating EMF and the current are virtual values, unless otherwise specified. Either 230 volt AC means AV is equal to RMS is equal to effective मतलब 230 volts है. Okay, AC ammeter and AC voltmeter read the RMS values of the alternating current and voltage respectively. They are called as hot wire meters, and the scale of DC meter is linearly graduated with the whereas the scale of AC meters is not evenly graduated because of heat is directly proportional to आई कॉस स्क्वायर। अगर हम लोग AC मीटर्स को भी इसके साथ रिलेट कर देंगे तो हमारे पास जो करंट है, करंट डबल होने से हीट जो है वो 4 टाइम्स हो जाएगी, इसलिए हम लोग उसको नहीं कर सकते। AC एमीमीटर को हम लोग कैलकुलेट नहीं कर सकते। नाउ वी हैव 3 components, that is resistor, capacitor and inductor. So we will take first component, that is resistor, a circuit containing pure resistor only. Okay, so in this figure you see that we have a resistor and we have a EMF, alternating EMF E is equal to E naught sin omega t. Okay, so the current will as the circuit is closed, the current will flow through this circuit, and the current is given by I is equal to E by R. Okay, then you put the value of alternating EMF, that is E is equal to E naught sin omega t, is equal to E naught sin omega t. You will get E naught by R sin omega t. If we replace this ratio E naught by R by I naught, that is the maximum current, we will get I is equal to I naught sin omega t. So this is the input voltage and this is the output current. This is the current. Okay, so you can see in these two equations there is no phase difference between the voltage and the current. It is sin omega t, and in both the equations we have sin omega t. Okay, so we can say that EMF and the currents are in the same phase. What is the meaning of same phase? When the current is minimum, the EMF is also minimum. When current is maximum, EMF is also maximum. So they are in same phase. You can see in this figure they are increasing with each other and decreasing with each other. Okay, एक साथ increase हो रहे हैं, एक साथ decrease हो रहे हैं. So they are in same phase. So we can show this using a phasor diagram. You can see here a phasor diagram. The current and the EMF are in the same phase. We represented them in a single line. Okay, and omega t is the angle. Okay, so in MCQ you will get 3 graphs, or you have one graph is there. You have to identify which component of electricity is there. You have one graph of any one, that is a capacitor, inductor or resistor. By seeing that graph you have to identify the component, which component is that. So see this and remember this phasor diagram, that is the circuit containing resistor only. Now if we take in only, the next topic is DC circuit, the pure. As we know that when we pass the current through an inductor, there is a self-induction. Okay, so due to this self-induction, an induced EMF which opposes the flow of current will generate. Okay, so the applied EMF is E is equal to E naught sin omega t, and the induced EMF in the inductor is given by minus L di by dt. Okay, by Kirchhoff's law, the sum of these two EMFs must be 0. So in order to maintain the flow of current, the applied EMF must be equal and opposite to the induced EMF. Okay, so induced EMF क्या है हमारे पास? E is equal to L di by dt, and supplied EMF क्या है हमारे पास? E naught sin omega t. Okay, so हम लोग इसको इक्वेट कर देंगे एंड क्रॉस मल्टीप्लाई करके हमारे पास डी आई आ जाएगा. डी आई इज इक्वल टू ई नॉट बाई एल साइन ओमेगा टी डी टी. नाउ इन ऑर्डर टू फाइंड द करंट we have to integrate this expression. Okay, as you know, E naught by L is constant. It will come out of the integration sign, and when we integrate sin omega t, we will get minus cos omega t by omega. Okay, now we have input potential as E naught sin omega t, but output as I is equal to I naught minus cos omega t. So we have to write this cos omega t in terms of sine so that we can compare. So minus cos omega t can be written as sine omega t minus pi by 2. Okay, so our current output current is I is equal to I naught sine omega t minus pi by 2. Okay, now we can compare the input and output, that is potential and the current. So there is a phase difference of minus pi by 2. We can say that the current lags behind EMF by pi by 2. Okay, the current lags behind EMF by pi by 2. What is the meaning of this? Current lags behind EMF by pi by 2. That is when potential is EMF is maximum, current is minimum. When current is maximum, EMF is minimum. They are moving like that. And in phasor diagram, we can represent it as EMF in the positive quadrant and current in the negative quadrant, and the angle between the EMF and current is pi by 2. So this phasor diagram shows that the current lags behind EMF by pi by 2 radian. Remember this phasor diagram. Now, when we apply AC to a capacitor only, when we apply AC to capacitor only, we E is equal to sine, and as we know that I is equal to dq by dt, and when we integrate it, I is equal to dq by dt, and when we put the value of q here, c naught sine omega t, we will get E naught 1 by omega c cos omega t, and in other terms we will get I is equal to I naught sine omega t plus pi by 2. Okay, now we can compare this EMF and the current. In this case, the current leads the EMF by pi by 2. So in phasor diagram, we can represent it like this: I in the second quadrant, and in the first quadrant, and it is separated by pi by 2. That is, here we see that the current leads by EMF by pi by 2. So remember this. Now these graphs are also important. In MCQ you may get this question. You have to identify the right graph, the variation of axle, that is inductive reactance. I forgot to explain. That is, when we write this equation in terms of I is equal to I naught is equal to E naught by omega L, whereas omega L is inductive reactance, the resistance offered by the inductor. Okay, it is represented by XL. So XL is equal to omega L. And likewise in capacitor, we know that XC is equal to 1 by omega C. XC is capacitive reactance, and it is written as 1 by omega C. Omega is the frequency and C is the capacitance. So this is the variation of XL with frequency. Okay, so we see that the inductive reactance is directly proportional to the frequency, so we will get a straight line. But in case of reactance offered by a capacitor, it is inversely proportional to the frequency. So the graph is like that. You must remember these two graphs. It may come in MCQ. Now, if we combine these three factors, that is resistor, capacitor, and inductor in a single circuit, we will get an LCR circuit. Okay, so in LCR circuit we have only phasor diagram. Okay, so if we draw all these components phasor diagram combinedly, you will see that the current and the voltage are in the same phase in case of resistor. Okay, and in case of capacitor, the current lead by voltage, and in case of inductor, voltage lead by current. So this is the phasor diagram. We can redraw this phasor diagram as VL minus VC is equal to VR, and we can find the effective or resultant of this EMF as E is equal to square root of V square plus VL minus VC ka whole square, and we will put the values of V is equal to IR, VL is equal to IXL, and VC is equal to IXC. So we will get the impedance, that is the effective resistance of the LCR circuit, as square root of R square plus XL minus XC ka whole square. Okay, this is the impedance, and the current in LCR circuit is given by I is equal to E by R square plus XL minus XC ka whole square. Okay, we have to remember this phasor diagram and this two expressions, that is the impedance and the current through the LCR circuit. No derivation is required. Okay, if and we can find the phase angle as x tan x is equal to tan phi is equal to XL minus XC by R. Okay, when we put the values of XL and XC, we will get tan phi is equal to omega L minus 1 by omega C by R. So from this expression we can find some special cases. If XL is greater than XC, that is omega L is greater than 1 by omega C, then the current lags behind the EMF by phase angle phi, and the LCR circuit is inductive. And if XL is greater than XC, the LCR circuit is capacitive dominant circuit. And if XL is equal to XC, the current and the EMF are in the same phase, and the impedance does not depend on the frequency of the applied EMF, and the LCR circuit behaves like a purely resistive circuit. And it is this third condition is called resonance. Third condition is known as resonance. So in resonance, you see that the XL becomes equal to XC. So omega L is equal to 1 by omega C, and we will get the resonant frequency as 1 by 1 by under root LC. Okay. So this is the graph. In this graph is very much important. In this graph, we have to find the correct options. R1 is greater than R2, R3 is greater than R3. Likewise, you have 4 options. You have to choose the correct option. That is, in this equation, you see that the first peak, जिसका जो एम्पलीट्यूड सबसे हाईएस्ट है, आई एम मैक्सिमम, उसका रेजिस्टेंस सबसे लोएस्ट है. ओके, ये चीज़ तुम्हें ध्यान रखनी है. ओके, वी हैव 10 minutes left. तो पावर इन LCR circuit, we can calculate the power, that is P into I, and in this expression we will get in this expression, if we solve this equation, we will get PAV, that is AC power, is equal to EVIV cos phi, where cos phi is called power factor. Power factor is equal to R by Z. You may get some questions based on this power factor. So what is power factor? Power factor is R by Z, and it can be calculated by the formula PAV, that is power is equal to E into I cos phi. Okay. Now transformer, that is very much important topic, transformer and generator. So what is transformer? Transformer is a device which converts lower alternating voltage to a higher alternating voltage, okay, current, and into a higher alternating voltage at lower current. Okay. So what is the principle? It is principle based on the mutual induction. Okay, most of the students write this principle, that is transfer based on the mutual induction, but some students write it will convert high voltage to lower voltage. It is not the principle, it's working. So first of all, what is a transformer? Transformer is a device which converts lower alternating voltage at higher current into higher alternating voltage at lower current, and the principle of transformer is mutual induction. It is a phenomena of inducing EMF in the secondary coil due to the change in current in the primary coil, and hence the change in magnetic flux in the secondary coil. Okay. You can see here in the primary coil we have a source of alternating EMF, and alternating EMF that is given by EP is equal to minus NP d phi by dt, and in the secondary coil the EMF is given by minus NS d phi by dt. Okay, when we calculate the ratio, that is ES by EP, we will get NS by NP, and this NS by NP is called K, where K is called transformation ratio, okay, or turn ratio. So we have two type of transformers. First of all, for an ideal transformer, we must have output power is equal to input power. Okay, this is the condition for ideal transformer, that is output power must be equal to input power, that is ES IS is equal to EP by IP, or we can calculate the ratio ES by EP is equal to IP by IS. Okay, and when we equate this by the number ratio of number of turns in secondary coil by number of turns in primary coil. Okay, and efficiency is output power by input power. Okay, for an ideal transformer the efficiency must be 100%. So we have two type of transformers, type of transformer and the step down transformer. Okay, so step down transformer we have number of turns in the secondary coil. Type of transformer में step down transformer में we have number of turns in the coil in the primary is greater than the number of turns in the secondary coil, but in step up transformer we have number of turns in secondary coil more than the number of turns in the primary coil. And you can see here in the step up transformer the ES, that is secondary EMF, is greater than the primary EMF, and the secondary current is less than the primary current. And in the step down transformer we have number of turns in the secondary coil less than the number of turns in the primary coil, and secondary EMF is less than the primary EMF, and secondary current is greater than the primary current. Okay, you must remember. So there are some losses in the transformer. This question may arrive in your exam also. Copper loss, that is heat loss, flux loss, eddy current loss, hysteresis loss. You just read that. Okay, so we have one question. A transformer having efficiency 90% is working on 100 volt and 2 kilowatt power if the current in the secondary coil is 5 ampere. Calculate the current in the primary and voltage across the secondary coil. So first of all we have given in this question the efficiency, that is 90%. When we convert it into decimals we will get 0.9, that is 9 by 10, and the secondary current is 5 ampere, or input voltage is 100 volt. So we just convert it into power, that is EP and IP, that is 2 kilowatt is given, that is 2000 watt. So by this formula we can calculate the input current, and efficiency we have output power by input power. Okay, now we will get the output power as output voltage as 360 volt by this numerical. Okay, next topic is AC generator. AC generator is very much important because it will come in 5 marks if it comes. So what is AC generator? AC generator is a device which converts mechanical energy into electrical energy, and its principle is mutual induction, EMI. And construction, you can see here in construction we have armature coil, 2 rings, brushes, 2 magnets. Okay, and in working at initial time t is equal to 0, where theta is equal to angle between the magnetic field and the area vector, and the magnetic flux is given by BA cos phi is equal to 1. So when we rotate this coil, the angle will change and it will induce a EMF. We have discussed earlier also during EMI chapter. So this EMI this rotation will generate the current. When the angle is 90 degree, we will get the maximum current, and when the angle is pi, we will get the minimum current. So this diagram is very much important, and you have to, whenever this question come, you have to draw this diagram with this graph. Okay, so remember this. Now one question. An AC generator consists of a coil of 50 turns and area 2.5 meter square, rotating at an angle speed of 60 radian per second in a uniform magnetic field B is equal to 0.3 Tesla between two fixed pole pieces. The resistance of the circuit includes that of coil is 500 ohms. So find the maximum value of the current drawn from the generator. What will be the orientation of the coil with respect to the magnetic field to have maximum or zero magnetic flux? Would the generator work if the coil were stationary and instead the pole piece rotates together with the same speed above? Okay, so the answer is we have n is equal to 50 times given, and a is equal to 2.5 meter square, it is given. So for maximum current we have to first calculate the alternating EMF, and it comes out to be, according to the formula, 2250 volt, and maximum current we know I naught is equal to E naught by R. It comes out to be 4.5 ampere. For the second question, maximum flux will be maximum if the coil is in a vertical position. On the other hand, the magnetic flux will be zero if the coil is in the horizontal position. जैसे अभी हमने ग्राफ देखा ऊपर, उसी ग्राफ के ऊपर बेस्ड ये क्वेश्चन है. अगर ये 5 मार्क्स का आएगा तो तुम्हारे पास एसी जनरेटर पूरा आएगा और एक न्यूमेरिकल आएगा, जैसे कि मैंने यहाँ पे दिखाया तुम लोगों को. तो अभी हम लोग 4 यूनिट्स कर चुके हैं. 4 यूनिट्स में हम लोगों ने 17 मार्क्स कवर किए हैं. तो होपफुली आप सब लोग इसको कर पाओगे, और इसमें जितने भी डायग्राम्स हैं, जितने भी इक्वेशन, जितने भी फॉर्मूले हैं, सबको याद करना है. कोई भी क्वेश्चन छोड़ के नहीं आना. कोई भी क्वेश्चन अगर तुम्हें नहीं आ रहा है तो उसमें कम से कम एटलीस्ट फॉर्मूला डायग्राम जरूर ड्रॉ करके आना है. यू हैव टू अर्न मार्क्स. ठीक है, हाफ मार्क्स अगर लेंगे तो भी हमें बहुत हेल्प मिलेगी. अगर हम लोग सिर्फ फॉर्मूला लिख के आते हैं या डायग्राम भी ड्रॉ करके आते हैं तो कुछ मार्क्स हम लोगों को मिलेगा, और हम लोग अच्छे से मार्क्स स्कोर कर पाएंगे. टाइम का ध्यान रखना है. टाइम मैनेजमेंट इज़ वेरी मच इंपॉर्टेंट. ओके, जैसे ट्रांसफॉर्मर है, जनरेटर है, इनके डायग्राम्स की प्रैक्टिस करो, इनके न्यूमेरिकल्स की प्रैक्टिस करो. ओके ओके, थैंक यू क्लास. थैंक यू वेरी मच फॉर अटेंडिंग माय क्लास. एनी क्वेश्चंस? Any questions? Okay, thank you.
Hello, sir.
Thank you. You can leave the class.